Hey, welcome to the Explainer. You ever run into one of those physics terms that just sounds super complicated, like radius of gyration? Well, stick around, because we're about to show you that it's actually a really simple and kind of powerful shortcut for understanding pretty much anything that spins.
Okay, so let's get right into it. Why is rotational motion so tricky sometimes? Honestly, it can feel like you have to memorize a million different rules for a million different shapes.
I mean, really think about it. Why is it pretty easy to spin, say, a basketball on your finger, but trying to get a bicycle wheel going, even if it weighs the exact same amount, feels so much harder? Same mass, so what's the deal?
Well, the secret isn't just about how much an object weighs, it's all about where that weight is. For that bike wheel, almost all the mass is way out on the rim, right? But the basketball's mass is spread out a lot more evenly, and that distribution, well, it changes everything.
Here's a perfect example to really see it in action. A hollow ring with all its mass stuck on the outer edge is way harder to get spinning than a solid disc of the exact same weight. That ring just naturally fights you more when you try to rotate it.
So yeah, all these different shapes can be a total headache. But what if? What if there was a simple trick to make them all a little easier to handle? Turns out there's a really cool idea for that.
Okay, so here's the thought experiment. Just imagine we take any spinning object, doesn't matter how weirdly shaped it is, and then we just magically squish all of its mass, every single particle, down into one tiny little concentrated ball of stuff. Like taking a big clay sculpture and rolling it all up into a single pebble. And here's the million-dollar question. Where exactly would we put that tiny ball of mass so that it has the exact same resistance to spinning as the original big, complicated shape did? There's got to be a perfect distance, right?
Well, that special distance has a name. It's called the radius of gyration, and we usually just call it K. It's that one single distance that perfectly captures the spinniness of the entire original object. It's a total game changer.
So how do we find this K value? Do we have to guess? Nope. Thankfully, there's a really simple formula that gives us the answer every single time. It's kind of like a magic key.
And there it is. K equals the square root of I divided by M. Now, don't let the letters and the square root sign freak you out. This is way, way simpler than it looks, I promise.
Let's just break this down real quick. K is that special distance we're looking for, the radius of gyration. I is something called the moment of inertia. That's just the fancy physics term for how much an object resists being spun. And M, well, that's just its mass. How much stuff it's made of. And you want to know the best part? The unit for K is just meters, or centimeters, or whatever length you're using. Because at the end of the day, the radius of gyration is nothing more than a distance. That's it. Just a length. Okay, enough with the theory. The real power of this idea is seeing how it actually helps us solve problems. So let's grab our new tool and try it out on a couple of examples you might actually see on an exam. All right, first up, let's find K for a solid sphere. We start with the known formula for its moment of inertia, which is I equals 2/5 mr squared. Easy enough. Now, we just plug that whole thing for I right into our new equation for K. And here comes my favorite part. See how there's an M for mass on the top and on the bottom? They cancel right out, and that's awesome because it tells us that K only depends on the sphere's radius, not how heavy it is. After that, we're left with a nice, clean answer. Okay, for example 2, let's flip the script and work backwards. This time, someone gives us the mass and the radius of gyration, and they want us to find the moment of inertia I. No problem. We just rearrange our formula a little bit to solve for I, which gives us I equals m times k squared. Then it's just a matter of plugging in the numbers, 50 kilograms times 0.4 meters squared, which gives us our final answer of 8 kilogram meters squared. See? Simple as that. Woo! We've covered a good bit of ground. So let's just take a second to lock in all the important stuff with a super quick recap. So, the big things to remember are the radius of gyration, K, is just a clever way to simplify complex spinning objects. Think of it as that squished mass distance. If you just remember that one magic formula, K equals the square root of I over M, you've got yourself a seriously powerful shortcut for blowing through rotation problems. All right, I'll leave you with a little puzzle to chew on. Which one do you think has a larger radius of gyration? A big, light hula hoop
or a small, heavy bowling ball. Think about where all the mass is located. Thanks for hanging out with me, and I'll catch you on the next explainer.